Welcome and hello. This is a video exercise in the FHWA hydraulic toolbox. I'm titling this exercise, How the Time Step Affects Detention Basin Results. So what we're going to be looking at is two parameters, two results in particular, the max discharge and the max volume that are calculated using the detention basin calculator. And we're going to have four different inflows, which are all going to be the same inflow, but have a different time step. So you'll see what I mean. Let's go ahead and get started. On the screen is the problem statement. So it's really just a question, really. How does the inflow hydrograph time step affect the outflow hydrograph? Because the outflow hydrograph results are based on the time step for the inflow data, as far as I can understand. So we're going to take a look at how that works and some of the results, both the numbers and also the plots as well. All right, so we're also given some basin data. The initial storage is 0. Here is the geometry of the detention basin. We're going to need all of that information. Here is the inflow in units of CMS versus time in minutes. That's the horizontal axis. And this 40 is supposed to be a 60. Sorry about that. And we also have some information about the standpipe. That is how water exits the detention basin. All right, so keep that information at your disposal. In fact, I'm just going to move it over here and get started with my hydraulic toolbox. So the calculator that we're going to be using here is the detention basin analysis. So click on New Detention Basin Analysis. You can also go right-click New Detention Basin Analysis. Okay, I'm going to rename this first calculator, and it's going to be inflow, comma, DT. Actually, no, we'll just call it base. All right, so you'll see what that means. Once I get this set up, I'll be making duplicates for 3 other calculators, most of which will have the same data, but I'll be changing the inflow data. So I'm going to double click to open up this calculator. First, what we're going to do is define the storage. So this is the geometry of the detention basin. I'm going to use the known volume option. So click that radio button and then define. Now, if we bring over the inflow data, we have our basin geometry right here. The elevation ranges from 50 up to 55 meters, and then the volume is in units of metered cubed. Let me just move that right here. Okay, that'll work. 1, 2, 3, 4, 5, 6. We only need 6 different points, so I'll do that. 6. And, I could copy paste from Excel because this was originally Excel, but there's so few data that it won't take too long to just key it in. Okay, so those are the elevations and the volume 0, 250, 800, 1400, 2400, and 4000. That looks good. Let's move this back up here. Click on the plot button. So there is that relationship, elevation versus volume. And I'll go ahead and close that and then click OK. All right, so that's good. I'll click OK. Next, we want to define the outflow discharge data. And we're going to click on Add Standpipe because it's a standpipe that we have data for. All right, so I've kind of repositioned the data on the screen here. Here's the given data over here to the right. So I'm just going to enter that data. The name standpipe 1, that is fine. We're only going to have one standpipe, so that's cool. The diameter is 1 meter. Then the weir coefficient and the orifice coefficient, I'm just using the default values here of 1.838 and 0.6. All right, height above the base elevation. Now the base elevation is, what am I doing? So this is supposed to be 50. Sorry about that. It's supposed to be the base elevation of the basin. Not sure why that was 1. And then we want the height above the base elevation to be 1 meter, meaning any water above the elevation of 51 meters will eventually flow out of the basin. So we're going to have, I guess, 250 meters cubed of inactive storage, I guess you could call it, subject to evaporation, but whatever. All right, so base elevation is 50 meters. Sorry about the number issue there. Height above the base elevation is 1. That's correct. So this data is all good to go. I'm not going to add any other discharge features, just one standpipe. I'll click OK. All right, so now we have our table that's been developed for the elevation and the storage and the discharge. Next, what we need to do is define the inflow data. And initial storage is 0. That's correct. The inflow data is what is going to change between our different calculators. Of course, we only have one calculator right now, but just letting you know, once we create other calculators, this is the button we'll be clicking on to change the data. So define inflow data. Okay, so I've got it repositioned again. So we have the given inflow data over here. The inflow goes from 0 up to 5 CMS, which peaks at 30 minutes, and then it goes back down after a total of 120 minutes. So the climbing limb is 30 minutes, and then the receding limb is 90 minutes. All right, so as for data input, the number of points that we need is sort of the bare minimum, is what I meant by base, is going to be 1, 2, and 3. I'll change this 2 to a 3. 0, the next time is 30, and then the final time is 120, just a triangular shaped hydrograph. And then inflow of 0 and 0 is correct for points 1 and 3, and then point 2 at time 30 minutes is going to be 5 CMS. So that's pretty straightforward. If I click on plot, we can just confirm we have the correct numbers, the triangular shaped inflow hydrograph. So let's go ahead and click OK and run the computations. So if I click on route hydrograph, here is the discharge numbers. And if you click on the plot, you'll see why I'm laughing. This is supposed to be the outflow hydrograph, but of course it's plagued by the fact that it only has a point at 30 minutes and 120 minutes, and for some reason 150 minutes. So I guess it gives an extra half hour or 30 minutes of data. If we plot that versus the inflow, we can see the two plots against each other. The blue line is the inflow hydrograph. The red line is the outflow hydrograph, which is called the routed hydrograph. So that looks pretty silly. I think you'd agree that this does not look natural. It looks artificial, partially because the DT is too large. In fact, if I go right click and then view the values, you can see that the routed hydrograph only has points at 0, 30, 120, and 150 minutes into the simulation. So I'm going to keep track of this peak outflow of 3.14 CMS. That's pi. And then also, I'm going to take a look at the storage curve and then click on plot. So just as the routed outflow hydrograph sort of looked artificial, so does the storage curve. We start at 0 volume, and then it goes up to around 3,300, maybe 3,400, and then back down. So remember this artificial looking curve. Here's the data. 3,354 is the max. I'm going to write that down in my results as well. And let's go ahead and change the inflow data so we have a little bit more precision and smaller discretization in the time step. So I've closed all of the windows. What I'm going to do now is just go right click and duplicate. This time I'm going to rename this calculator. Rename, instead of base, I'm just going to say DT equals 10 minutes. Okay, so I think might know where I'm going with this. I'm going to double click. Here is the calculator. I should have all the same data. So wait a second. Let me delete this. Double click. Okay, maybe I had to save it first. Okay, I guess I'll just redo this. Okay, so I added the data back in. I'm going to go File, Save, call this Project 2. Yes, overwrite. Okay, so fingers crossed. Let's try to duplicate that data now. Okay, so I've duplicated it. Let's rename it and then open it up. So I'll call it DT equals 10 minutes and right click Detention Basin data. Okay, that's good. So I'm guessing I just had to save the data before I could make a duplicate. So the more you know. No need to change the geometry of the basin. No need to change the outflow structure, that standpipe that we had. But here is the inflow data. This is definitely something we want to change. And what I'm going to be doing in the remainder of this exercise, here's my Excel file, here's the basin geometry, and then here's the 4 different inflow hydrograph data. The shape of these hydrographs is all the exact same. The only difference is instead of 3 points, now I'm going to extend it to what is 13 points. So 4 points representing the inclined limb and 9 points, 10 points, because we're using this point at the top for both the receding limb and the rising limb. So the shape should be the same. And then for dt equals 5 minutes, I'm going to do the same thing, but the time step is 5 minutes. And then finally, if there's time, dt equals 1 minute. All right, so I just interpolated the numbers so that at time equals 30 minutes, the inflow is 5 CMS right here and right here. And where is it? Right here. So just trust that that's correct. So this is what I want to copy to my clipboard. The inflow for dt equals 10 minutes will have 13 points. Copy and move that out of the way. So instead of 3, it'll be 13. Tab off and then just paste those in. If I click on plot, It should look exactly the same as what we saw before. So that's cool. No change there. And then click OK. And voila, that's all we really have to do for changing the input data. I'm going to click on Route Hydrograph. And now we have more numbers. See, we have a total of 14 rows of numbers. Okay, it looked like it was 13 on the input data, but they're adding one additional time step at 130 after 120. That's fine. Let's go ahead and plot it. Now this is the outflow hydrograph. Looks a lot better and smoother and more natural than what we saw earlier. So the peak outflow is going to be probably this point right here. I think that's the 50-minute mark. We can just look at the numbers here. And yep, 3.772 CMS. Let's take a look at the storage curve now. So again, we have more numbers than just 3 or 4. If I click on the plot, again, a much smoother, more realistic storage curve than before. Peak storage is now going to be around, what, 2,800 it looks like. Let's see what we got. 2880. Okay, so I'll take note of that as well. And we are ready to move on to our ET equals 5 minute. I'm going to go ahead and save this just for good measure. Right click and duplicate the 10-minute and then rename it. Change the 10 to a 5. Okay, click off. Double click to get the data. Click on Define Inflow Hydrograph. Now, instead of 3 points, I made a copy of the 10-minute one. Okay. Not sure what to make of that. We'll see what happens. So we're going to have 25 data points. I'm just going to paste those in here. Click on the plot button to make sure it's the same shape. It is. And then click OK. And let's see what we have for our results. So here are the results. Here is the plot of the routed hydrograph. In fact, I'm going to take a look at the plot hydrographs together so we can kind of compare the difference between the blue, which is the inflow, and the red, which is the outflow. I could have done this with DT 10-minute time step calculator, but I just didn't. So we can see how, when the blue is above the red, that's when we have increasing volume in the detention basin. When the red is above the blue, that's when the volume is decreasing. So we know that the max volume is at the time where there's the intersection, which is probably about somewhere between 50 and 60 minutes. We can also get the results by going right click, view the values, and then let's see here. So between 50 and 60 minutes, here it is, 3.56, 3.75, 3.7 right here, 3.757. I got 3.76. I'm going to close this. And then for the storage curve, let's see what that looks like. Storage curve. Here are the numbers, and here's the plot. It looks smooth, just like the 10-minute time step curve. In fact, it looks a little bit smoother, to be honest. We have the maximum storage occurring right about here, which again is probably going to be 50 or 55 minutes. So let's do the right click and view values. So we scroll down a little bit. We have a maximum right here at 50, 28, 24. All right, one more to go. So let me close this, close, and hit save, and then right click, duplicate, right click, rename. This time let's go with 1 minute time step. So let's open that up. Let's move this over here. Define inflow hydrograph. I'm copying the data from my Excel. I'm going to need 121 points. So just put that in there and then paste and then plot to confirm. Looks good. Okay. Okay. And let's take a look at the results. I'll just click on plot the hydrographs together. Okay. Looks pretty much like what did last time. I'm not sure decreasing the time step from 5 minutes to 1 minute makes much of a difference, at least not visually on this plot. But let's go right click and view the values. So we're looking at somewhere just around 50 minutes again. If I'm looking for the maximum outflow, I scroll down and here we are. It is, right here, 3.756. I'll just say 3.77 again. That's 52 minutes into the simulation. In fact, the time of the peak outflow would have been another interesting parameter to keep track of, but we're good with just keeping track of the outflow hydrograph, peak volume, the peak flow rate, as well as the peak volume storage curve. Here are the numbers. Here's the plot. This looks a lot smoother. And then let's take a look at the numbers. Right click, view the values. I'm scrolling down here to around 50, 52 right here, 2802. And that's the maximum storage in meters cubed for inflow hydrograph using a time step of 1 minute. Okay, so That was pretty interesting. I think the takeaway from this exercise is to make sure you're using a time step that is sufficiently small to get accurate data. Clearly, what we saw from this first plot here was not accurate, or at least not nearly accurate, because as we decrease that time step, here's the 5 minute data, here's the plot for the hydrograph. Oops, okay. You know what? Is this not saving? One second. Plot the hydrograph. Okay. Well, if you were watching this video, you saw what it looked like. I still have some learning to do as how the calculator works. I think I need to be saving something at a different time. And when I get that figured out, I'll leave a comment or I'll leave something in the description about it. And I can only assume that values are becoming more accurate and more precise as DT approaches zero. So the max discharge or the outflow, the routed hydrograph out leaving the detention basin started at 3.14, 3.77, 3.76, 3.76. So as far as max discharge goes, I think it's fair to say that DT equals 10 minutes is accurate enough. That's a precise enough time step because dropping it down to 1 minute, we're only improving it by zero point zero 0.01, which is what, 0.3%. And then for max volume, that decreased from 3354 to 2880 to 2824 to 2802. So as far as max volume goes, what I learned is that we probably need to be doing a DT to 5 minutes or 1 minute, but I think 10 minutes is a little bit too far off because you're off by what, 78 divided by 2880. That right there's a 2.7% difference. So I guess I could call it a 2.7% error, assuming DT equals 1 minute is the correct answer. So that's something else to consider if you're dealing with max discharge versus max volume. You may need to be a little bit more precise and have a slightly smaller DT if you're dealing with the storage values like max volume. All right, well, that's it for this exercise. What we did was look at the relationship and plots of the outflow routed hydrograph and the storage plot for the same inflow hydrograph, but using different time steps.